Okay, so what we have seen is we said that there are two terms, if you recollect, was casual heat gain Q, I think we did QCS plus alpha I by H naught into U into A sigma of this some j aj ij, because this will be all average radiation, this is average, this is the part of heat gain, and this we are calling as some q bar, right, q bar, and this must be equals to sigma of u j, here j going from some 1 to m, and here u j a j going from j going from let us say 1 to n, where n surfaces are m surfaces receives radiation and there are total n surfaces into TOA minus TIA bar plus CV into TOA bar minus TIA bar. Therefore, I can find out TIA bar, I will come to that, but before that let me just, what was the expression for CV? CV was, we said 1/3 n into VR, n into VR, right, approximately CV was equals to 1 by 1/3 n into VR, right, that is what we did, because that is the coefficient for ventilation heat transfer, all right. So, CV bar we use because we said n would change, n can change from time to time, and we are taking it like this because we are taking all mean heat coming in. So, it follows from there that I will have TIA bar can be written as TIA bar will be written as TIA bar will be written as Q bar, because I am calling this as Q bar divided by sigma u j a j, j going from 1 to n plus C V, right. So, TIA is on the other side and TO TOA minus TIA would be this, Q divided by all this equals to TIA minus, so TIA minus TOA or whatever it is, or plus TOA whatever it is. So, plus minus TOA. So, from this I can find out. Now, let us solve an example problem that will make things clear. I just repeated the previous equation was here, just let me again clear it up, this portion let me just remove, that is what I said, Q bar was this plus the casual heat wave that I called as Q bar, that I call as Q bar, and Q bar this let me also remove just before we solve the equation. So, Q bar is equals to this equation I can set in, and from this everything is known except for this one which is unknown, except for this one which is unknown, right, this is what is unknown, and from this equation Q bar is equals to this plus this, I can find out TIA. TIA I can find out, I can set the algebra, or if I write TIA minus TOA, whatever it is. So, I can find out TIA from algebraically I can find out. So, let us solve an problem. Supposing I have a room 6 meter by 5 meter by 3 meter with one external wall, I made it simplified, one external wall, because otherwise too many calculations you have to do. I just want to show you how you do it. On the long axis has a single glazed window 4.5 meter by 2 meter. Okay, red is a better color, again let me use red, facing south. Calculate the mean internal temperature given that TOA bar is 17 degree and the mean global irradiance on exposed wall is 180 watt per meter square, something like this. Assume alpha for the solid wall is HO is 9, U is 0.7, U of the window is 5.6. Glass will also have a U, right, because it will transmit because there is a temperature difference, glass will allow radiation to come in, but there is a temperature difference, due to that also heat transfer will occur, and glass is very thin. So, it will allow most of the heat to come in, right. For unit temperature difference, the heat that will come in is very large, that is why it is 5.6 compared to that of the wall. Assume 2 air changes per hour of the room, that is mean, and all adjacent room be at the same temperature. Solar gain factor for glass is theta, this is theta. So, it is something like this, it is something like this. Oh, and right, it is something like this. I have a room. How much is the values given? How much is this? 6, 5. Okay, so this is 3 meters, let us say, and this side there is a room. There is a room. This side there is a room. There is a room on this side as well, and there is a room on this side. Only one side is exposed. Only one side is exposed. So, all heat gain will occur through this, and we are assuming this room, and this room are all at the same temperature. So, that my calculation gets reduced a little bit. So, this is 6 by 3 meter wall, 6 by 3 meter, and it has got a window, 4.5 meter. It has got a window. So, 4.5 meter by 2 meter facing south. I mean, my drawing is wrong actually. This also is, there is a room, this side is room, this is south, this is north, this is south, this has got a window, this has got a window 4.5 meter by 3 meter, 4.5 meter by 3 meter, okay, 4 something like this, 4.5 by 3 meter window is showing, all right, that is what it is. So, 2 meter, sorry, 2 meter, so it is partial only, not full. So, 2 meter window is there on this side, the sun's radiation will fall onto this, and this average is given as 180 watt per meter square. Am I clear? So, let me just again do this, let me just do this. The room is something like this. Right. This is the north side, all this side same temperature, same T, same T, same T. So, no heat transfer. So, no heat transfer. Only this side, and it has got a window of this kind, maybe something of this kind, 4.5 meter by 2 meter window is here. There is some sort of window here, this 6 meter, this was 3 meters, and this 5 meter and all that. So, this is the room actually, and this must be receiving radiation, this must be receiving radiation, and also there is a temperature there. So, U of this portion of the wall is given as 0.7, U, this is got a 5.6, U is equals to 5.6 for this window area, and we got to calculate out first, conduction heat transfer, right. So, we will calculate out conduction heat transfer through conduction heat transfer. So, volume of the room is 6 by 5 by 3, 90 meter cube. Now, air exchange is given as 2. Window area is 9 meter square, 4.5 by 2. Area of the wall is then, exposed wall, 6 into 3 minus 9, that is a solid, 9 meter square solid, 9 meter square glass. And I bar is given as 180 watt per meter square. Mean heat gain through the wall will be UA alpha I H naught, so which is 0.7 U. A is 9 meter from the opaque portion I am looking at. This is given as 0.4. This is I bar is 180 and HO is given as 9. So, this comes out to be 50, right. This comes out to be 50. Casual heat gain is neglected. casual heat gain is neglected, but there is a gain through the glass, which is AI theta. So, AI bar, A is 9 meter again, this is 180, and theta is given as 0.76. So, this. So, you can see the total heat gain is 12.1231.2 plus 50.4. This is heat gain, right? And that must be dissipated if the mean temperature has to remain constant, right. So, Q is 1281.6 watt. Q is 1281, this sum of these two is 1281.6 watt. CV, 2 air changes is given, 2 air changes is given, right. CV is 2 air changes is given. So, 1/3 NVR, so 1/3 2 into volume of the room is 90, right. So, it is approximately 60 watt per degree centigrade CV, CV into delta T, and UJ AJ 0.7 into 9 plus the glass portion 5.6, sum of the two. So, this comes out to be, this comes out to be, sum total of this two would be how much? 60 is this is 6.3 and this is 50.4. So, this comes out to be 12.81 etc., etc., and using the formula TI is 17 is the outside mean. So, 27.9, this is fairly high, too high it is showing, actually does not matter because it is a hypothetical problem, not really, only one wall is open, outside is 17 mean, inside mean would be significantly higher if all this heat has to be dissipated. In fact, this 180 value seems to be high, I mean one could have reduced this. So, that is how you can calculate out the mean inside temperature in an unconditioned building, you can calculate out mean temperature in an unconditioned building. We have not taken the fluctuating part so far into account, sorry, steady part we have looked into. So, mean room temperature, I am just rewriting this equation, generalize this Ti is equals to TO plus Q total, where Q T bar stands for QCS plus QR, which was basically AI theta, which was actually AI theta plus alpha I by H naught, alpha I by H naught into UA alpha, because this is the excess part of it. So, this is the Q, QT, and AU is the sum of this CV bar. That is what we have found out, that is what we have used just now. So, room temperature at any instant actually the sum of the mean and the fluctuating component. So far we have found out the mean inside temperature, but we got to find out the fluctuating component also. So, this is the fluctuating component. T swing, this we call as T swing, this we call as T swing, So, this T swing, we have to find out T swing, right. So, T swing we have to find out, this we call as T swing, we got to obtain the T swing. Now, total fluctuating energy gain at the environmental point due to any particular excitation frequency is given by total fluctuating heat flow. If I want to calculate out, this will be given by, first of all, fluctuating ventilation transfer. We have taken mean, we have not taken the fluctuating component. So far we have not taken the fluctuating component. Then casual heat gain, solar heat gain through the conduction gains and radiation from the opaque bodies, both. So, solar radiation through the glasses, all fluctuation we have to take it out. So, each one of this terminology, let me give an expression for all of them one by one. QFS is the fluctuating heat flow due to solar radiation on opaque surface, first term, opaque surface, right. I have taken the I average, the excess value over the mean is a swing. I at any point of time minus I mean, I call it I swing at that particular time, I swing that point, right. Mean plus there is a fluctuating term. So, that is what it is. So, similarly, due to this there will be heat transfer through the opaque bodies, which will be actually alpha this multiplied by divided by H naught multiplied by U. Here a little bit of complication will come, I will explain this, right, because it's conduction through the opaque body I have to take into account. QFC is the fluctuating heat flow due to opaque surface conduction only. This just let me remove this first, it is confusing. So, QFC is the fluctuating heat flow due to opaque surface conduction fluctuation, right. How we calculate, we will come to that. This part QFC is the QFS is opaque body solar radiation, FC is the opaque body conduction fluctuation, because there is a temperature fluctuation outside. QST is the transparent surface solar gain. We have taken AI theta earlier, now the swing part of it I got to take. So, again this I swing T is equals to I T minus I bar, which is the mean. So, that is the swing part. So, due to this swing there will be some solar gain transfer. Transparent surface conduction due to fluctuation, transparent surface conduction gain through the glass conduction gain. Casual heat gain fluctuation, we have taken mean all the time, additional that we have to take it, because Q C T minus Q bar C is equals to Q C T, casual gain, right. So, that is how we find it. So, this is all these are fluctuation above the mean. So, you have to take the values now, fluctuation above the mean, and this is a ventilation or infiltration fluctuation gain, ventilation or infiltration fluctuation gain, over the mean. We have taken a n bar, we took in earlier cases 2 for that for that example. Now, I will have n varying from time to time. So, CV will vary, CV is equals to basically 1/3 n into VR. Now, this n will keep on changing, so that I have to take into account. Let us see how we do it. This was through the opaque body, and RO stands for 1 by HO. AI, remember this is for the solar radiation falling onto opaque body, and solar excess was, if you recollect, it was alpha I bar, which I am writing as solar radiation T minus phi, there could be T at a given T I am writing this, divided by H naught, that corresponds to excess temperature, right, multiplied by U A mu. Now, what is U A mu? Mu is what? U divided by U swing divided by U. So, mu U is nothing but U swing, ratio of fluctuating heat coming in by outside temperature, right, for unit temperature, right. Now, this is the temperature fluctuation, because additional temperature fluctuation is this multiplied by mu U or U swing will give me the amount of heat, fluctuating heat that will come in per unit area. So, this must be multiplied by area. Now, U swing is written as mu U. So, you see the mu U A, and I am not dealing with complex things anymore, because I am taking absolute values. Now, I am using the quantities, how much is the quantity will come, but I got to take the time lag, because the temperature fluctuation which has occurred phi d hours earlier will now cause some real heat to come in now. So, T minus 5, T is the current time minus phi d corresponding to decrement factor, phi d corresponding to decrement factor corresponding to this mu corresponding to U swing this I have found out. So, this is instead I could have written HO instead of so this part is the temperature. This is because the temperature swing would have taken place. This is the swing part of it. Fluctuation of the solar radiation would have taken place for due to that which has occurred earlier, the heat will come now. So, this is the time lag, this is 1 by H and AI Ui, mu I is nothing but this gives me U swing into A. So, that is how I am just calculating this, right. So, this is how I am calculating. Sum up for all the surfaces which receives radiation, sum up for all the surfaces which receives radiation, that will give you the fluctuating conduction gain through opaque body due to solar radiation impinging onto it, solar radiation impinging. And direct conduction gain because of temperature is simply TO swing of the outside temperature, same phi d because it is related to decrement factor d phi d, that is a phase lag, time lag due to phi d, right. That is how you calculate it in terms of time, because T minus this I will take it. The temperature swing has taken place earlier outside, now it is coming in, because it will store and then transmit, store and transmit, right. And this term stands for, this is the U swing multiplied by area and T swing. So, therefore, that is the fluctuating component of FCT, that is the FCT, right. That is the conduction gain because of outside temperature. ISO is, that is what I said, this this I already have mentioned you. So, that is what I have mentioned you earlier. And well, for the glass you can do a little bit of complicated, you can complicate it, or for this one QST you can do a little bit of complicacy because it can absorb now and transmit later. So, one can do a little bit of complicacy, but we do not do it that way. We simply write solar radiation, you can complicate this, but instead we take an equivalent theta which takes into account of, like the question that was asked is that what is the difference between theta and alpha. Alpha is for opaque bodies, the absorption. Alpha plus tau is what gives this, tau is what is transmitted, but this occurs only in case of transparent bodies. The glass, for example, is transparent to the solar radiation. So, it takes all the heat radiation, light radiation both in, right. So, in that case tau alpha theta contribute tau contributes fully to theta, but some of the incident radiation falling onto glass will be also absorbed because it gets heated up itself, and part of it radiate outside, part of it will actually transmit inside, right. So, the alpha part of it is also taken into account in theta. So, theta actually encompasses anything part of the alpha, part of that is absorbed, but whatever is reflected is rejected out, that is left out. Whatever is transmitted is allowed plus part absorbed, right. So, this theta is also actually a function of angle of incidence and some more complications there, and there will be a lag from the time of absorption to the transmission. Direct transmission is instantaneous, radiation falls onto it, it comes inside straight away, but whatever is absorbed by the glass, it will transmit it somewhat later. So, you can have a time lag for that, but that will be very small because glass is a thin member, it will not store for long and part of it will only come in. So, what we do is we do not complicate it that much, we assume there is a theta swing, or you might assume a fixed theta value, both swing as well as steady single theta value. So, A theta T, you can take it like this, or simply you can take it as A I theta T, A I theta T. So, casual heat gain, simply this, you can find out how much is the swing in casual heat gain. There is nothing, because that is from inside the room. So, if you can find out every hour what is the heat generated, how many people are sitting, typically how many let us say lights are on, fans are on, how many heaters on, etc., and hourly changes would be there, used up time, sometime it will not be used. Take the average, that is the mean that you have used in finding out the mean temperature. Fluctuation above that value is a fluctuating component. So, that is the total at a given time minus the mean, that is the fluctuating component, right. So, for significant, if there is a if there is a radiator, for example, you have a heater. So, this equation could be somewhat different. If there is a radiation, because some of this radiation might go to the wall and come back and things like that. So, for significant radiant component, the equation gets complicated, because there is a time lag also associated with this, how much is being radiated, and if there is no, usually in tropical countries you will have summer conditions, there will be very little radiation component. You will not, you will not have a heater, you will not have a heater. But if you have something like lights which have a very high heat component, usually that would be less usually. So, that you can again ignore and treat it simplified manner. This was for the glass transmission. There is no conduction transmission through the glass, and it will not have any time lag. Conduction heat gain through the glass, because by and large it is almost instantaneous. U value of the glass we took it. So, U into that is what we take. So, this is how we calculate out all except ventilation heat transfer, except the ventilation heat transfer, right. So, constant CV we have already taken care of. Now, if CV is varying, it becomes a little bit problematic. It becomes a little bit problematic in the sense that QBT at any point of time, I will be writing as CV into TO, TOT, assuming constant CV throughout. I have not taken variable ventilation at the moment. Variable ventilation is little bit complicated. We will take it later on. At the moment, let us assume it to be constant, CV is constant. So, at any instant, the ventilation heat transfer will be given as TO mean plus TOT fluctuating, fluctuating part. So, this is the outside temperature total minus inside temperature total at any time. Now, you see this we have already taken into account, that is this minus this we have taken into account. This we have not taken into account. CV into TO bar T minus TI swing T, I have not taken into account. This minus this already taken into account in mean calculation. So, this the heat gain due to ventilation has to be taken into account in this manner. For constant CV steady ventilation, infiltration heat transfer was taken like this. Remaining unaccounted portion is this much, and that you must take into account. So, assuming uniform room temperature, fluctuating component of temperature is the ratio of, okay. So, you take all this into account, sum them up. I will tell you the philosophy, next class I will tell you about how to calculate out the inside swing. So, sum them up. Now, I have given you all formula for calculating all the heat that is coming in, right. Assume that all this heat will go in increasing the fluctuating component of the temperature, because we have admittance, and admittance is defined as the amount of heat flux required to cause unit temperature swing inside. Total heat coming into the room, and we assume constant room temperature. So, swing in the room is any point, we are not distinguishing temperature from one corner of the room to the other, that is again an approximation. There can be some variation, but we are assuming as if it is constant. In that case, the amount of heat that will come in will cause the temperature swing all across the room. So, I can now sum them up and use my admittance concept to find out the temperature swing. How do I find out the heat coming in? By using decrement concept and all simple ones like ventilation and all, they are fairly simple. All casual heat gain, they are fairly simple, simply fluctuating component I have calculated, and all fluctuating component I assume that they have gone increasing the temperature swing. So, admittance is get linked now, because admittance is defined as the temperature, I mean the amount of heat required to cause unit temperature. So, if I know the total heat gain, how much is the temperature swing, that I can find out. So, we will look at that in the next class, and maybe solve a problem. But remember, all that we have done is we have assumed a constant ventilation. We have not varied the ventilation. If I vary the ventilation, then it becomes far more complex, and inside equation will be something like this. I will start from this side back into the next class. Okay. So, that is it for the today.